So in this video, we'll discuss conservation of angular momentum, which is very similar to the principle for conservation of linear momentum. Remember that for conservation of linear momentum, as long as we had an isolated system, one such that the net force acting on the system was equal to 0, then this meant that we had a change in momentum was equal to 0. So it meant that our initial momentum was equal to the final momentum. And just how we saw previously that it takes a torque in order to change angular momentum, if we have the net torque acting on a system, then this means if the net torque is equal to 0, this means that our change in angular momentum is also equal to 0. So we have the initial angular momentum is equal to the final angular momentum. And we treat angular momentum like before and after, just as we did with linear momentum. So we run through our solutions in a very similar fashion. The only difference here with angular momentum is that, so if the initial angular momentum equals the final angular momentum, this means that I initial omega initial is equal to I final omega final. Now with linear momentum, it was a little bit difficult to change the mass, right? With linear momentum, and you remember this was mass times velocity. And so the mass more or less remained constant, and it just happened to be a change in velocity. Unless, depending on the type of collision. But with rotational inertia, it's very easy to change your mass distribution. Remember, rotational inertia is not just how much mass there is, but it's how that mass is distributed about the axis at which it rotates around. And so if you look at this picture here, there's this guy with he's holding some barbells out, and he's on this rotating platform, rotating around in a circle like this. As he has these barbells out on the far edges, his mass distribution is very far from his axis of rotation. The axis which he's rotating around is right here, and so the mass, he has a lot of mass far from it. And remember that the rotational inertia is the sum of all this mass times how far away it is squared. And so he has a very large moment of inertia when the mass is placed far out here. And he has some certain rotational momentum, some angular momentum associated with this his rotation and his rotational inertia right here. When he brings his arms in, though, without really changing the mass, only changing the way the mass is distributed, then this rotational inertia becomes much smaller, and therefore it must be made up by increasing the rotational velocity. So although he was rotating very slowly in the initial condition, we'll call this I for initial, and the final condition, by bringing his arms in and reducing his rotational inertia, he increases his rotational velocity through conservation of angular momentum, which, as long as we have no net torque acting on the system, angular momentum is always conserved. Some cases we might have seen this just in day-to-day life. If you ever watched any figure skating, then you have a figure skater rotating maybe about an axis through one of her legs here. So she's rotating around like this, and so she has some omega, and she has some rotational inertia associated with how her mass is distributed, so she has some initial angular momentum. As she brings her arms in closer to the axis of rotation, then she is decreasing her rotational inertia. And since the total angular momentum must remain constant, she must have an increase in rotational velocity. So she spins faster as she brings her leg in and brings her arms in, and she spins slower as she moves her arms and legs out. Another instance you might be familiar with this is doing a flip off of a diving board or a rock or something. Um, when you flip, you might tuck in. So when you pull in and you're rotating about maybe an axis that goes right into the screen, right through here, through the center of your body, and you're rotating like this. When you're tucked in, you have a very small rotational inertia, right? So you have a small rotational inertia. Initial, we'll just say we have like a small rotational inertia, and so you have a large rotational velocity. And then when you stretch out later on, your final angular momentum, you would have a much larger rotational inertia. So you have a large I final, but then you have a very small rotation. So that way the product is still the same. So we still have initial angular momentum is equal to final angular momentum. And these products are equal to each other. So just one thing, I mean, I guess one way that angular momentum is different than linear momentum is that it's very easy to change your mass distribution. You don't have to change your mass to change your inertia. You only have to change the way that mass is distributed. So there's a few more things we can play around with. So conservation of angular momentum. This is so long as the sum of the torques acting on the object or the system are equal to 0. Then we have initial rotational inertia times initial rotational velocity is equal to your final rotational inertia. That's your final angular velocity. And this is conservation of angular momentum.